So here we're going to continue to look at our trig form of complex numbers, and what I want to look at is, let's assume that z is equal to this trig form of a complex number, and I'm curious about z squared. Well, that's really z times z, and on the very last video we learned how to multiply complex numbers. So it would essentially be this complex number times itself. So it would be times r times cosine theta plus I sine theta. Now, we did that on the last slide, except we didn't have so many variables. The idea was you multiply your r's, you add your thetas. Well, r times r is going to be r squared. Theta plus theta is going to be 2 theta. So I have a relatively straightforward, it's relatively straightforward to be able to raise this to the second. It means r is squared, and I've got a 2 in front of each of my thetas. And if I wanted to do z to the third, well, then I would have to do one more multiplication and have to multiply by z one more time. And if I multiplied by z one more time, all right, this is again right here. This is just z, right from the very top of the problem. Well, I'm now multiplying. I do exactly what I said we do. We multiply our r's. R squared times r is r cubed. And I add my thetas. 2 theta plus 1 theta is going to be 3 theta. Plus I sine 3 theta. So I'm hoping you could make a prediction. Let's say I wanted z to the 7th. All right, I would hope you don't have to write this 7 times. I'm hoping you see a formula. You would just take your r, raise it to the 7th, take your theta, multiply it by 7, and you would easily be able to raise the trig form of a complex number to any power. All right, that idea has actually been developed. It's called de Moivre's theorem. All right, and this is exactly what the last slide is saying. If z is equal to the trig form of a complex number, right, then Zn is relatively easy to calculate. You are worried about raising r to the n power, and you put n times theta in front of both, and then you will have, I forgot my I right in here. There is an I in that formula that I mistakenly left out. And other than that, then it's just an application of this theorem. So if I want to raise this to the 12th, all right, so I hope you see the immediate problem with this is it's not in trig form. I don't have my sines and my cosines. So I need to get my sines and my cosines by getting r and by getting theta. So I get r by doing the square root of -1 squared plus the square root of 3 squared. Well, that's 1 plus 3, the square root of 4. So my r value is 2. I am going to get my theta value by setting up tangent theta is equal to radical 3 over -1. So where is theta equal to negative radical 3? That is going to be at 2 pi over 3. Now you got to ask yourself, are you in the correct quadrant? And we are. This is in quadrant 2, and my answer is this would be in quadrant 2. And 2 pi over 3 is also in quadrant 2, so great. We can write this in its trig form, 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3. And what we are concerned with doing is taking this whole statement and raising it to the 12th. So the easy way to do this is 2 to the 12th and times cosine 12 times 2 pi over 3 plus I sine of 12 times 2 pi over 3. And my final answer here, 2 to the 12th times the cosine, that's going to be 24 pi over 3. We're going to call that just 8 pi, so that would be cosine of 8 pi plus I sine of 8 pi. Close the parentheses, that would be your answer. Oops. That would be your answer. If you really felt so, you could type 2 to the 12th into a calculator it would be 4,096. So if you prefer that in front, I'm totally okay with that, but 2 to the 12th is just as good. 4,096, and then you just copy over this parentheses that have the exact same pieces in it. If you have any questions, bring them to class tomorrow. I will see you then.